So this is where we were yesterday. I was, not yesterday, on Friday. We're talking about how to come up with the oxidation number of elements. Either if they're by themselves as an element, that would have an oxidation number of 0. When you have a compound, the oxidation numbers of the C and the two O's add up to 0. So oxygen would be -2, carbon is +4. When you have a polyatomic ion, you can figure out what the oxidation numbers are. Knowing oxygen is almost always -2, and therefore the nitrogen is going to have to be whatever, when you add it to +6, or not positive, -6, what would nitrogen have to be when you add it to -6 that would give -1? That would be a +5. So we should be able to come up with oxidation numbers. That reaction I was talking about on Friday, I love that mug. That mug just makes me smile. A picture of a red ox.
Do you own that mug?
I do. Yeah.
That's kind of sad.
I had.
Very happy, actually.
Yeah, makes me happy.
Will that make me a better chemist if I buy that?
Might. Yeah, it might. Okay, so anyway, the chemical equation that I was showing you on Friday, I just made it FeCl2 so it would be easier to balance. This is FeCl3. I think this is the more correct oxidation number of iron. I think it does make a +3, not just a +2. But just remembering what we had to do. The iron by itself has an oxidation number of 0. The copper and the chloride, copper, because the chloride is -1, it's just a monatomic ion, we figure out the copper is +2. Over here, the chloride is -1 again, so the chloride just winds up being a spectator. It doesn't do anything except just be there. It doesn't change at all. The iron, however, did change. It's a +3 here. And then the 3 coppers wind up with 0 oxidation number. Now what does that mean? That means the iron was present as a metal and it dissolved. It became a +3 charge, got rid of 3 electrons. The copper went from +2 down to 0. It gained electrons. When we balance the equation, it should take care of making sure that the number of electrons that were transferred is equal. So there's 2 irons that went from 0 to +3. That's a total of 6 electrons that were lost by the iron. There's 3 coppers that went from 2 down to 0. That's a total of 6 electrons that the copper took in. Yes? So the electrons have to be accounted for, just like the atoms have to be accounted for. When we balance an equation, we're balancing the atoms. But with redox chemistry, we have to pay attention to the charge as well. Not only do atoms have to balance, charges have to balance too. Now, just a couple of terms. We're not going to use these terms right away, but you may come across these terms when you're doing the homework problems. First of all, you'll recognize a redox reaction anytime something's oxidation number changes. And clearly, we have, and just remember, synthesis, decomp, single replacement, and then combustion. All those will involve redox reactions. So that's not too hard to recognize when you have a redox. You do have to figure out oxidation numbers of everything. But here's the thing that is kind of unfortunate. We have to know this is something that's commonly used in chemistry. The concept of a reducing agent and an oxidizing agent. So in a reaction, the thing that's oxidizing is giving off electrons. That's allowing somebody who wants electrons to have electrons to take. So the thing that oxidizes in a reaction is called the reducing agent. It's like it's helping something else to reduce. That gets confusing and frustrating to people. And you may wind up as one of those people that gets frustrated by that. Yeah, because it's the opposite word. The thing that oxidizes is the reducing agent. Then the thing that in the reaction that reduces is considered the oxidizing agent.
So the one reduced was one that gains electrons?
Yes. Yep.
Yeah, what is the thing that you use to find which one is like losing?
Leo the lion. Grrr! Gaining electrons is reduction. Yep. Yes?
Why is Fe 0?
Oh, Whenever you have a neutral metal or any neutral element, it's oxidation number 0. So like O2 would have a 0 oxidation number. Zinc, Zn would be 0. Magnesium, Mg is 0. Only if they have a charge. Like this is an ionic compound, it's a metal and non-metal, so you figure out what their charges are. But when you have an element that's by itself, that's not attached to anything, it's going to be 0. That's neutral. So just throw these terms out here, and now we get to the balancing. Jazz?
Oh, I was going to ask what's that noise?
Yeah, I think that's the heating cooling system. I don't know whether they're trying to heat the building right now or cool it, but they send water through these pipes, and then it blows the either hot or cold air on us. That's what you hear. I want to show you a chemical equation, and just mention that this is a type of equation that we would have to use a different technique for. Something is off about this equation that makes it impossible to balance conventionally, like the way we normally balance. The term I use is we normally balance by inspection. We say, okay, we have one BR there and we have 2 there. Okay, so we put a 2 in front of this BR. We have 1 MN and 1 MN, so we just leave the MNs alone. We have 4 O's. See what I mean? What do we do with the O's? We can't balance this by inspection because we have O's on one side, but what just happened? How do we start with O's but not end with it? Where did the O's go? Well, it turns out that they did go someplace. It's just not in the unbalanced ionic equation. And so this is going to be our first task to try to learn how to balance this. And this happens with redox. It says in the problem, and by the way, this is not even a chapter 4 problem. I'll tell you that. We're going to learn how to balance redox reactions, but it's not even going to be helpful to us until we get to chapter 18. Now, Mr. Hell and I both feel that if we didn't show you how to balance, it's not really even worth talking about redox right now. We could have just left it out. But it's not bad to see how to do it now, and then we come back to it in chapter 18, which is about in March of next year. We'll be able to just pick this right up and say, oh yeah, I remember how to balance redox reactions. There is a process to it. It's an 8-step process. And if you came in at the beginning of class and you were looking at what I had that now I have erased on the board, you're like, what? That looks like a lot of work. And it does seem like a lot of work, but I'll tell you that balancing redox reactions, this method we're going to use is called the half reaction method. It is actually kind of fun to me because I personally am a linear thinker as opposed to a random thinker. I like to have a place to start and then follow a series of steps and then have a place to end. And in doing that, you wind up, there's no difficult ones because you're just doing the same thing over and over. Like stoichiometry is the same way. Yep. You just wind up doing the same thing over and over in stoichiometry. Yep. You got to get to moles so you can use the coefficient ratio. It's the same thing all the time. So I'd like to introduce you to the 8-step procedure for the half reaction method. We'll come back to this, but go ahead if you
Full
start.
reaction method, 16 steps.
No, there's no full reaction method. 8's the maximum. I will tell you this too. If you went to Khan Academy or other tutoring sites, you may actually learn a different way to balance these things. And you might say, oh, that's easier than Moore taught us in class. And that may be, but I think this, even though it's a lot of steps, this is so systematic that everybody can learn this, and you'll find it to be quite easy. As not easy as it seems at the beginning, you will all, I think, just find it to. It's just nice. It's a nice thing because everything seems to fit together. So let's take a look. So I say use the half reaction method when the chemical equation is too complex to balance conventionally. Balance using inspection.
How do we know when to use the half reaction method?
That's what it's saying. If you can balance an equation without doing this, this is going to take way longer than just checking, putting some coefficients in there and checking. So if you can do that in an equation, then do it.
Is this the hardest part of the chapter?
At first you might think this is hard, but I don't think you're going to find this to be that hard. I'm not sure what's the hardest thing in the chapter.
Is there a test that Tuesday then?
The test is going to cover this chapter and chapter 5, and the test is on Halloween.
Oh.
What? What?
You just hate
Yeah.
kids.
Wait, that's fine. Well, like, at least we
Listen.
go trick or treating.
A test on Halloween is 1,000 times better than a test the day after Halloween. You with me?
However, can you?
Oh my God! He's trying to pack grades in.
What's that?
And take our grades with him.
We don't have school that day.
Nice.
Yeah. So that's even better. So yeah, Halloween's on a Thursday this year, and it's the last day of the quarter. It just happens that it does turn out to be
He
Halloween.
wants our grade to plummet right before the quarter.
Yeah. So expect an impossible test, so that I can just laugh like a nasty witch.
Do you guys ever do anything study for Halloween? Like
This is actually
dress
decent.
up? Like, what's
Blue
your
clothes.
We have in the past.
Oh, okay.
Sometimes the science department will come up with a theme, and that's kind of fun.
So more of the time, grades
Yeah.
would be
Wait, last year didn't you like dress up as the blue pillar or something? Was that-
Yeah, last year was Blue Pillar year.
Yeah, I remember
Yeah,
that.
yeah.
Do you ever like?
It's kind of
When
fun.
people come for like trick or treating, you give them like weird chemistry stuff, like butyric acid. Chemistry problems to get the candy.
I should do that to people I know.
Yeah.
Like, oh, here you go. Enjoy your candy now.
Feels
That's really funny now. That'll be good.
Okay, let's look.
All right, let's do this. All right, now let me have your attention. If the reaction occurs in acid, this is what we do. If it occurs in a base, then we have to do something different. Now, it's not totally different. The half reaction method is going to be pretty much the same every time. In base, though, you're going to have one more step than we would if we're in acid. So we'll start with this. We'll just focus on reactions that are in acid today. Tomorrow I'll show you what we do if it's in a base.
Why does that use a hat reaction?
I'll show you. So pretty much what you're going to write down, everything that's under the shade, is not going to make any sense until we do an example.
Wait, is this a step?
Yeah. Yeah, you want to identify who's oxidized and who's reduced, and then we're going to write what we call two half reactions. One's going to be for the oxidation, one's going to be for the reduction. It sounds like it's really scary and hard, but it's not.
Lose electron to oxidation.
That's right. Go ahead and growl the big grr if you want to.
Which girl?
That girl will need to be at a
Just say
C4
girl.
All right,
with
it's
a
fine.
volume of 14 decibels.
You can leave it to me to do the self-humiliation.
Let him do it.
Okay.
Just say girl.
So, all right, now let's stay together and try to get through this. Here's what I'm hoping to do. In the last hour, I ran out of time, so I'm going to try not to do it this time. Once you have the half reactions written, you want to balance everything in the half reaction separately, except for hydrogens and oxygens. We're going to do those last. So balance the elements in each half, other than H and O. Now, if it's in an acid, if the environment around the reaction is in this acid environment, what is there a lot of? There's a lot of water. There's like an infinite amount of water. And what else is there a lot of? It's an acid. Hydrogen ions. Right, acids give off hydrogen ions. So the reaction has a lot of these hydrogen ions just kind of floating around. And reactions usually will take advantage of that and use some of the hydrogen from the acid environment. That's what happens here. Now, sometimes you're going to have oxygens that come off, especially off of a polyatomic ion. They don't just stay as free oxygen ions. They'll get absorbed by hydrogens and make water molecules. So we're going to balance oxygens, not just with O's, but we're going to use water molecules.
So the amount of water molecules.
Yeah. So like if you have 3 oxygens on this side and none on the other side, then put 3 water molecules on the other side to balance the oxygens. Now that takes care of the problem that we had over here. You know how we lost the oxygen? Where did the oxygens go? This is an acid, so it made water molecules. We're going to see water in the products eventually.
So you add 4 H.
Yes, you'd add 4 waters on that one. Yep. After the oxygens are balanced, Then sometimes hydrogens get thrown in there and introduced because you got water molecules. So we'll have to balance the hydrogens using hydrogen ions.